Here we have section 4.4, and in this case we're looking at the fundamental theorem of calculus. Oops, well, if I can spell it right. Fundamental theorem of calculus, FTC. So there we go. Okay. And it's a good name for it, because in the end, yes, this FTC is the truly fundamental thing in calculus, I think. I'm going to backtrack a little bit. The textbook goes through this and uses the mean value theorem, but I think really thinking about integrals as summations is summations of changes is a very powerful thing, and thinking about the approximation aspect of it and all that is also very important. So we didn't look at 3.9, but in section 3.9 they mention this idea of a differential, and not a real big deal here. We just want to look at the idea and get the notation. So if I am zoomed way in on a function, so there's some function f of x, then you know, I'd have this tangent line that looks almost just like it. And if I wanted to look at a change, and I could start that change right at that point where the tangent line is, or a little bit on the lower end here or something like that. But if we take a particular delta x, okay, that's our change in x. Now this is the real life change in x from wherever we're talking. And then we have our change in f, or change in y, which is the real live amount change there. Now, because the tangent line is so similar to the function, well, then what we would also know is that that change in f is approximately the same as taking our slope. Now, what's our slope? Well, that's f prime at our given x value, and then times the delta x. Okay, so, you know, think about that just with a straight line, right? All we're saying here is, you know, if I had some delta y and some delta x, that our slope is delta y over delta x. Now if I solve for delta y by multiplying both sides by delta x, I get that my delta y is the slope of that straight line times delta x. Well, that slope of the straight line is our derivative, and there's the delta x. And so when we're talking small enough items, this is really, really close. I mean, you know, it's always, we can say it's approximately the same, but when they're very close together, they're definitely very close to the same. And now if we blow it up and exaggerate a little more, so there's my tangent line, there's my actual value of f, and so we're saying that whole thing there is our change in f. What we're going to call this thing here, we're going to call this df, or the differential of f. And that, as we pointed out up here, is just our derivative, okay, the slope of our tangent line, times delta x. Except now, in this case, we're just going to call it dx, okay, the differential x, differential of x. Now, here's a subtle point. Notice this and this, they are actually just different names of the same thing, okay? So the dx is any positive value, just like delta x could be any positive value. So these two are really one and the same. You know, I can say dx or I could say delta x. However, on this end, you know, if I'm talking about delta f or delta y or something like that, the function change here, those are not the same. Okay, here, this is an approximation. So we have that delta f can be approximated by df, which is our f prime of x dx. Okay, so that's the idea of a differential. And of course, if we zoom in close enough and make dx or delta x, so delta x or dx here small enough, then this quantity here and that quantity there are going to be very, very close. And in the limit, they're going to be the same thing. And so, well, actually in the limit, they all become zero, I guess. But so we have df is similar to a change in delta f. And so I just wanted to, you know, get across this idea of that approximation using that calculation, and the fact that this dx is nothing special, it's just delta x. Just when we start talking about these small approximations, we change to the dx instead of the delta x. It's a, you know, kind of a, I guess in some sense, a rhetoric thing, right? We're trying to get a certain point across, and so when we see dx, we tend to think of much smaller changes, I guess, and so that helps get that point across. Okay, so there we have this idea of the differential and delta x. Now, let's just look at some function. And now this time I'm going to go with an uppercase f of x for that function. And there's a and there's b. So we have, if we look at it this way, all right, there's f at a and there's f at b. And, you know, I could get the full change here by taking lots of little incremental changes. All right, I could find that change, and then I could find that change, and I could find that change. And if I call this one, say, delta f1, and this delta f2, and delta f3, all the way up to finally some delta fn, right? If I sum all those up, I get this distance here, all right? Because I took that distance, that distance, that distance, and so forth, and I summed them up. So we can write that down as f of b minus f of a, that's that distance on the y-axis, that is equal to the sum, I equals 1 to n, of delta fi. So I'm just adding up each of those little stair steps up the function and saying, well, how far did I go? add them all up, I get that distance f of b minus f of a. And so we can call it that delta fi. But you see, then that, if I make n large enough and so forth, this is very closely approximated by the sum I equals 1 to n of dfi, the differential. And that is equal to the sum I equals 1 to n. That differential, that was f I prime at some xi, and then times dxi. Okay, again, those, each of these changes don't have to be the same size. We didn't have to move the same amount on the x, but there's that. And remember, that's really just a delta xi. Okay, just a new name for it. But now, this is right. This is an approximation. However, if we take the limit of this thing and let n go to infinity, or the other way to look at it is let the maximum dxi go to 0, then we'll actually get that value there. We'll get this, right? In the limit, this and this are going to become equal. And so we can write f at b minus f at a is equal to the limit. And again, we can either say something like n goes to infinity, or we could say the magnitude here of the dxi goes to 0 of our sum I equals 1 to n of f prime at x fi at xi dxi. And remember that that's these dxi, that's just a delta x. But that limit is a definite integral. That is the integral from a to b of our function here, f prime of x dx. And there is our fundamental theorem of calculus, is that we can evaluate a definite integral using its antiderivative. Okay, so that's what this says. So just as a quick example, suppose we have, and we'll make this, relatively simple case here. If our f of x is, say, something like x squared, which would mean our f prime of x is 2x. If we have something like that, then it would say, and actually we tend to use it this other way, is, I can evaluate that definite integral from, let's go from 0 to 3 of 2x dx. The theorem says all I have to do is take that antiderivative, x squared, and evaluate it at 3 and subtract it evaluated at 0. Now the way we tend to write that is something like this at this stage. So here is my antiderivative of the 2x, and then I keep my bounds around with the 3 on top and the 0 on the bottom, and then what this says to do in this notation here is to take 3 squared minus 0 squared, and so I get 9. Okay, now let's check that with the geometry. So this was 2x, Okay, so we had that line. We went out here to 3. So this height was 6, because that's 2x. And we could think of that definite integral as that area. And so now, I look at that and, oh, it's a triangle. And the area is 1/2 times the height, 6, times the base, 3. So that's 18/2, or 9. So you see, this fundamental theorem of calculus allowed me to see this area here without using the geometry. I mean, I could just use antiderivatives. But more importantly, what you want to realize is that what we're doing here is we're adding up a bunch of changes in f, right? So, I went too far there, right? We are adding up all these changes in f here, and that, in the limit, is what got us to this definite integral. There's nothing here that says we're talking about area or anything like that. So, area is an interpretation of the definite integral and the fundamental theorem of calculus and so forth, but it is not the definition. It's an interpretation. And it's a darn nice interpretation. But in the end, what you really want to get is that when you see this definite integral here, okay, like what we have here, when you see that definite integral, remember that what you're doing is you're adding up a bunch of little things that look like this, so they're a 2xi times a dxi. Okay, I'm adding up a bunch of things that are some function evaluated at a point times a little small jump in the x. Okay, so a little small jump in the x, a little bit of the function, and I can interpret that, as, here's my dxi, and then the slope here happens to be my 2xi. And so what this is approximating is a change here. Okay, now we call it, say, df or dy, so I could call it dyi. Okay, but it's approximating some actual change that's maybe that big or something like that, or a little bit smaller than the dy. But at any rate, it's just approximating a small change, and then we're adding up lots and lots of things that look like that. And that's a key to actually using the antiderivative work and definite integrals and so forth, using our calculus to solve some interesting problems, is that we need to think about adding up a bunch of these small changes that can be modeled this way. Okay, a function times a little chunk of x, the x-axis. Okay, so there's one example of using the fundamental theorem of calculus where we need our antiderivative, but once I got my antiderivative, we just plug in the 3 for the upper limit, subtract off the lower limit, and we get an answer. It becomes very much just a arithmetic and algebra thing, just knowing those rules. Now, notice with antiderivatives, general antiderivatives, we added a c, but notice what happens that if I added a c there, so integral from 0 to 3 x squared dx, oops, not x squared, 2x, then if I said, oh, well, this is the function x squared plus some arbitrary constant, we'll just call it any constant, like that, And then I evaluate that at my 0 and 3 and do the subtraction. Then you see I get 3 squared plus c minus 0 squared plus c again. But that minus is going to make that a minus. And the constants just cancel out. And so they don't really matter. We just get the 9. Okay, so worrying about that arbitrary constant in a definite integral is not necessary. Okay, we just go with the basic antiderivative with no arbitrary constant, or in other words, the arbitrary constant is 0, and there is our there's our definite integral, and we use antiderivatives to do it. So that is the fundamental theorem of calculus, and that is a big time theorem.